Okay, so we're going to continue on the laser. So I hope you saw the video that I have posted in the group chat, the laser that we have in the other lab that I'm working on. Okay, so you could see there at least three type of laser. So as I've told before, one type of laser that we have are the solid state one, and this is still the one that is widely used with three-level device where usually the one that you commonly use is the so-called ruby crystals. Okay, so ruby crystals is your aluminum oxide that contains approximately small amount of chromium distributed along the aluminum lattice site, which give it the red color. Okay, so the ruby color is really by a chromium. So the chromium ions are the one that is the active lasing materials there. And in early laser, usually the ruby was machined into a rod about 4 centimeter length and 0.5 centimeter in diameter. And you have a flash tube, which is a low pressure thinner lamp that's coiled around the cylinder to produce the intense flashes of the light. Okay, and we're going to get it around 694.3 nanometers. So the pumping was discontinuous. Okay, you can produce a pulse beam from this, and continuous wave ruby sources are now commonly available. Okay, so the experience that I have, I think, with the ruby is with the mirror system when I was still in graduate school. Okay, where we pump it and then try to use other, we could say, nanometer by just pumping it, or we could say get some pulse reading that we have. Now, aside from the ruby, okay, the NDYAG laser is one of the most commonly wide used solid state laser. So if you remember, this NDLYG, it consists of neodymium ion in a host crystals of yttrium, aluminum, garnet. So as you could see, all crystals use gems, right? Okay. So this NDYAG offers advantage of the 4-level laser. So last time we have the 3-level and the 4-level laser. So it's much easier to achieve the population inversion compared to the ruby laser. And it has a very high radiant power output. So if you're going to look at the laser that you have here, okay, so you have a mirror here, a fuse switch, and then you have the polarizer, and then there's a flash lamp. So there's a YAG rack that you have there. Okay, so this is where you generate your what we call laser. So as you see, laser usually you put the mirror and then you invert it, and then you try to what we call reflect it until you get all, okay, of your population there, okay, to the high excited, or we could say excited state or high energy level. So you pumping it there, and then I think this what we call conversion that you have here. You're going to have this laser output, okay. And there are, we could say, gas lasers. So these devices are of 4 types. So the one that you have is the so-called neutral atom, okay. So when we have this neutral atom, the classic example that we have here is the helium neon laser, okay. So this is the most common of all the so-called gas laser. So it's a continuous laser pump by an electrical discharge. So the lasing transition that you have here, okay, occur between the neon energy levels while the helium is added to increase the pumping efficiency. Okay, so it, it is most widely used because of its low initial and maintenance cost. It's really, we could say, high-end, expensive, okay, to maintain a laser. So for you to have a system of it, it's really high maintenance. And the thing is, you have to use it from time to time, or else there's going to be problems. So that's the problem that we have in the lab. Since the pandemic, we seldom lace the system that we have. So we're worried if one day we decide to use it, then it will not going to lace. So it has a great reliability, and the good thing about it is a low power consumption. So as you can see, the electric supply that I have shown you, okay, we have a special electric supply that we have to what we call included in the setup. Okay, it's due to the high power consumption that is needed, okay, to power it, and we also need to have a water system to make sure that we can at least uh, maintain the temperature, if you can generate high temperature gas. So the most important of its output lines is at 632.8 nanometer, and it is generally operated in the continuous mode rather than what we call the false mode. So if you're going to look, okay, at the laser system that we have here, so you could see there's a polarized output of the neon, helium neon laser. Okay, so again, you have the power supply that you have here. There's an anode area and the cathode area, so there's discharge tube. So that's where you have your lacing thing there. It's just air, okay? And the way you look at this one, the discharge tube is terminated with end windows filtered at the Brewster's angle. And thus there's no reflection that occur at the windows for light polarized with the electric field vector in the plane of the figure. And the orthogonal component is partially reflected on each path and quickly becomes an insignificant part of the output beam. Now, the one that I usually use that I haven't shown you, that's an argon lamp laser. Okay, so there are ion laser in which the active species is argon. Both of them are argon. One is at 514 nanometer and the other one is at 488 nanometer. So it produces intense light at this what we call region, and it's an important example of an ion laser. So that's the laser system that I have shown you in the video. Okay, so you only have one, we could say, system there. Okay, the difference that you have is the light source. The laser is the one that is different. So the idea there is whatever laser system I need, I just turn on one of them. You cannot use them at the same time because they will go on the same, we could say, instrument. So it's just like we just use different line source. Okay. So this laser is also a 4-level device in which argon ions are formed by an electrical or radio frequency discharge. So the required input energy is high because the argon atoms must first be ionized and then excited from their ground state with a principal quantum number of 3 to various 4p states. So you could see, I don't know if you see the power system. I have to, what we call, turn it on, and then after we're done, I have to turn it off. Okay. And in the, what we call, power supply that we have there, there should be a water line that is included there. If there's no water line, the laser system will not turn on. Okay. Many times it happened to me because why is it not turning on? So something might be wrong. And then I realized that there's no water. Okay. So later active occurs when the excited ions relapse to 4s state. And if we're going to look at this, what we call the system. So argon is what? A noble gases. So the output, the power that you have here is several watts. Okay. But it can get you to as high as 150 watts. So the most reliable laser usually is argon and helium neon laser. Okay. Now, the other things that we have is the next thing that we have is the so-called nitrogen laser. Okay, or the carbon dioxide and nitrogen lasers. So each of them are still what we call gas. So the medium that you have is either of the two gases. Okay, so for the nitrogen laser, it must be operated in pulse mode. Okay, because pumping is carried out with a high potential spark source provides intense radiation at 337.1. Now you might say, why do we have to know this? Because there's different lines for this laser system, and it depends on what line are you going to what we could use. Okay, so in this what we call the nitrogen laser. Okay, if you're going to look at this, so you have here the so-called Blum lane pumping circuit. So in this, what we call illustration, you have a high current discharge that passes briefly. So it's 10 to the 5 ampere with a lifetime of 1 to 5 nanoseconds for the laser tube containing the nitrogen gas. So this produces an inverted population, and the lasing begins from spontaneous emission, and the inverted population depletes rapidly. So because of the high gain, as you could see here, there's only what? One mirror opposite the output. So the peak output power is as high as megawatts. And the pulse duration is a few nanoseconds with repetition rates from 1 to 60 hertz. Now, the output here has found extensive use for exciting fluorescence in a variety of molecules and for pumping dye laser. Okay. Now, the thing with this, what we call, if you're going to use this laser system, you have to be very careful, especially depending on the nature of your sample. Because sometimes it can burn your sample if the power is too much. Okay, so you have to what we call take that into consideration. Now, the carbon dioxide gas laser is used to produce a band of infrared radiation in the region 900 to 1100 wave number. Okay, so if you're going to look at this laser, once upon a time, it's the most powerful continuous laser available because the output power is several kilowatts. Okay, have been obtained and can be pumped by collisions with the electrons or the resonance energy transfer from added nitrogen gas. So the nitrogen laser or the laser output from the CO2 laser is of course in a series of CO2 rotational lines with the vibrational transition. Now, the last type that we have is what we call the excimer. Okay, kulang ng C. So if you have an excimer laser, these are usually from a mixture. Okay, a gas mixture of helium, fluorine, and one of the rare gases, argon, krypton, or xenon. So the rare gas there is usually electronically excited by an electrical current, then reacts with the fluorine to form the excited ions that we call excimers. Okay, they are only stable on the excited state. So since the excimer ground state is unstable, rapid dissociation of the compounds occur as they relax while giving off the photons. So you only have this population inversion as long as pumping is carried out. And they are useful because of what? The line 351, 248, and 193. Okay? Now, another group of what we call lasers are what we call the dye laser, and they have become an important radiation source in analytical chem because they are tunable over a range of what we call 20 to 50 nanometer. Okay, so what does tunable mean? Anyone? So when you say tunable, you can adjust it. Okay, tunable lasers usually it's easy to adjust, and if you can adjust the laser, so that means you can use it at a certain range. Okay, so dye lasers have that. So the bandwidth of a tunable laser is typically a few hundreds of a nanometer is what we call, or less. And the active components that we have here usually are dye, okay? Lasers, they are solutions of organic compounds capable of fluorescing in the UV, visible, or infrared region. And dye lasers are 4-level systems. So the lower energy level for the laser action is not a single energy, but a band of energies arising from the superposition of the large number of closely spaced vibrational rotational energy stations on the base electronic energy state. Okay, so when you have like what we call dye lasers, they are pumped optically by a flash lamp or another laser. So this is where sometimes we hate doing it because you have to pump it with what we call another laser. Okay, and the pulse operation occurs with what we call flash lamp pumping, or by pumping with the pulse laser. So usually you use either the nitrogen or the NDYAG or an excimer. Okay, and if you're going to look, okay, the schematic for this what we call dye laser. So maybe this is the one that can explain it. Okay, so usually this is the laser that you pump. So there's a mirror there. So the dye laser pumped by nitrogen laser. So the beam expanding telescope increases the number of the groups of the grating, hit the beam, and decreases the power density so as to avoid damage by the grating. So tuning is accomplished by rotating the grating. So that's what makes it tunable, because you have what we call grating. Okay, and tuning of dye laser can be readily accomplished by replacing the non-transmitting mirror shown previously here with a monochromator equipped with a reflection grating or the lit growth type prism, which will reflect only a narrow bandwidth or radiation into the laser medium. And the peak wavelength can be varied by rotation of the grating or prism. Okay, and emission is then stimulated for only part of the fluorescent, namely the wavelength reflected from the what we call monochromator. So that's what we call the good thing about this what we call dye laser. Okay, and if you're going to look at the characteristics of the laser that we have, as you could see, the radiation that you have there has significantly different properties from radiation emitted by the other sources. So they are highly directional, pure, coherent, and of high radiance. Okay, and the directionality of the laser is direct result of the resonant cavity. So only waves that propagate normal to the mirrors oscillate. And as a consequence of this laser radiation can be accurately transmitted over a large distance, okay, to the spot on the moon and back. That's how it is. So that's why sometimes in the lab, when we're doing the laser, we try to play it. We just use what we call mirror. Okay. So in the laboratory, the directionality of laser simplifies the alignment of optical materials and enables samples in a remote location to be So one problem if you have what we call the laser is the tendency for you to misalign. And it happened to me when I was what we call new in using the laser. Because when you try to align them as much as possible, you do it one at a time in the mirror. So I think what we're doing with my groupmate during that time is we're moving parts, more than one part at the same time, to the point that it was misaligned. Yeah, I told you before that one time we aligned it, and there's a stray laser that came out that produced like a black spot in the wall. So it only shows that we're not what we call the able to align it correctly. Okay. And spectral purity is a result of the resonant interaction of the medium with the pop source. And the visible region is fairly routine to achieve line width on the order of 0.01 to 0.01 to 0.1. And laser radiation is classified as a coherent radiation. So it's said to be temporal coherent if for a given point in space, there's always a constant phase difference between the amplitude of the wave at two successive instants in time. And the final aspect of this laser radiation that makes it different from conventional radiation is the high irradiance. Okay, its power. They can achieve irradiances that are 4 to 10 orders of magnitude larger than those conventional sources. And that's also that you need to be careful, because sometimes that power or irradiance that you have, that may destroy the sample, like if you're working with biological stuff, like protein. Okay, so there's a direct consequence of the power and the directionality of the laser. Now, there's also this chemical laser. Now, they don't have optical or electrical pumping that's necessary. So what happens is there's a chemical reaction that produces the molecules in the excited state. And if the population inversion is achieved, you can have lacing for a specific transition. And hydrogen fluoride laser is the best known example here, where lacing occurs by the vibrational transition. Okay, so there's an electrical discharge used to produce the hydrogen and fluorine atoms. So it's from HF. So how are you separate that to produce the atom? Okay, you add energy, and the chemical reaction H2 produce with F atom produce excited HF and H. Okay, so you have the excited HF. And then we also have this what we call diode laser or semiconductor. So the population inversion occurs between the conduction band and the valence band of P positive negative junction diode. Okay, so in a semiconductor laser, the stimulated transitions of the electrons between the conduction band and the valence, the stimulated transition of the electrons from the conduction band to the valence band are responsible for the laser action, and stimulated emission results from the electron hole combination. Okay, so the frequency emitted here is directly related to the band gap energy. Various semiconductor compositions can be used to give the different wavelengths. Also, since the lacing occurs between the bands, these lasers can tune over small intervals, so it's also tunable. Okay, and typical materials that we have here is gallium arsenic, which laces at 0.84 micrometer, and lead salt diode, which plays in the mid-IR region. Okay, so infrared lasers can achieve very narrow line width, but must be operated at low temperature, 10 to 20 Kelvin. Okay, so the output powers of these are what we call dye lasers. So So this is usually used at very low temperature. Okay. And for a given composition, tuning can be achieved by just changing the diode current, which hits the diode. So this causes the refractive index to change that alter the effective cavity length. Then the tunable range that you can have is 20 to 50 wave number. So those are the different laser systems. Okay. And I hope in the near future, when you encounter them, you already have some sort of a knowledge how the principle of the laser can be. Because I was a little bit overwhelmed when I first encountered them. Okay, because I never saw a laser before, and there are, if I'm not mistaken, 3 laser systems during the grad school that I have. And if I'm not, the crystals that we have in the mirror system, they call it the mirror system, is a titanium sapphire. Okay. Now we're done with what we call the line sources. So we're going to go now in the sample containers. And we all know the classic, what we call material that we use. So these are what we call the cells or the cuvettes. So in UV absorbance spectrophotometer, spectrofluorimeter, usually you use a cuvette. And the one that we usually use are what? The quartz, right? And if you're going to look at this quartz, you can use it in the UV region. So the cells in the cuvette, that's the one that hold the sample, and they should be made of material that is transparent to the radiation. Okay. So if you're going to look at this, these are the region, the spectral region for the materials for cell windows, lenses, and what we call prisms. So the pure silica that we have there, the quartz, so this is the region that you can use it. Now, in addition to that, okay, you also use the glasses, the silicate glasses, but it's only applicable until the 300 region. Okay, so they can be employed in the region 350 and 2000 nanometer. Okay, and then in the visible region, you have what we call the plastic container. So it's not included here, but in the visible region, okay, in the colored region, that's where you're going to use. And I'm not sure if part of your experiment in the instrumentation is differentiating the cut-off window of this one. So how are you going to see them if you have like that? So usually, if I'm not mistaken, you can see everything like that for the quartz. For the other one, it's just like this. And for the other one, it's just like that. So that means you cannot see in this region that material, which is the plastic. And you cannot see in this region the what we call glass. Now, for the IR, it doesn't have to be transparent. Okay? Even if it gets dark or black, you can still what we call use that cells. And the one that's commonly used is the sodium chloride. But as I have told you, what's the problem with the sodium chloride? If you're using AQ sample, your NaCl can be solved. So the option that you have there in the lab, we have a silver chloride cell window. Okay. And if you're just doing what we call pelletizing, the one that we usually use is what? KBr powder. So you try to mix, okay, your what we call sample with your KBr. So question here, before we go on this, what we call transducer. So when we're talking about transducer, these are what we call the detectors. So we have the light source, we have the monochromator before, and then we have the sample. So once you put, okay, your sample and you let the light source pass through the monochromator and the sample, the next parts of the optical instrument that will go is what we call the detector. And the earliest, I think the eye is the main detector that we have. But what's the problem if we rely on the eye? Eye is usually not reliable. Okay? So aside from the eye, the earliest detector for spectroscopic instrument are the photographic plate and the film. But nowadays, there are many modern detectors that are used to convert radiant energy into electrical signal. Okay? What's the role? What do you call this stuff that convert the light radiant energy into what we call an electronic signal? So usually, that is the role of your transducer. Okay? So transducer is a device or mechanism that converts one form of energy into another. So in this case, radiant energy into an electrical signal. Okay, so transducer is the one that converts radiant energy into an electrical signal and have almost totally replaced the detection device that we have known before, the photographic plate, film, or the human eye. Okay, so if we're going to look at these properties of a transducer, usually this is the ideal transducer properties. Okay, it should have high sensitivity, high signal to noise ratio or low noise, constant response over many wavelengths. So this is a wide range of wavelengths. And in addition, we want it to have a fast response time. So high sensitivity, so as much as possible, we want to see as little amount of the sample, okay, to show some electrical signal. And high sensitivity also means low noise because you want to have a high signal to noise ratio so you can differentiate what is the real signal and the noise. Okay? You want it to be broadband. You want it to respond to a wide range of wavelengths. Because if the signal that it has is limited to a certain region, then it's not going to be applicable in many samples. And of course, you want it to have a fast response time. You don't want to wait hours before you collect the signal. Okay? And ideally, you want it to be what? To have a response of 0 if there's no light present, or what we call low dark current. If there's no light, the signal is equal to 0. And as much as possible, you want the signal to be proportional to the radiant power. Okay? Now, in addition to this, what we call low dark current, many real transducers, they exhibit a small constant response known as what? Dark signal. Okay? in the absence of what we call radiation. An instrument with transducer that produce a dark signal are often equipped with a compensating circuit that reduce, okay, the dark signal to zero. Now, you want it to be rugged, cheap, and simple. Okay? So, we're going to talk about the different radiation transducer. So we say radiation transducer because it converts radiant energy into an electric signal. Okay? So we could say there are what? Two general types of this what we call radiation transducers. And if we're going to look at this, okay, it can be either what? A photon transducer or a thermal transducer. So if we're going to look at the difference of this one, well, maybe one way to look at this has something to do with what? The region where you're able to detect them. So as you could see, most of these photon transducer or detectors are in the UVBs and near IR region. Okay. Now, for most of the thermal, they are all almost in the IR region. Okay. The only photon detectors in the IR region is the so-called photoconductor. So, if we're going to differentiate here, so this one responds to what? Photon. So all photon transducers, usually, they have an active surface that absorbs radiation. While thermal transducers, they what? Usually they respond to, anyone? So I think that's the main difference between what we call these two. Okay? The photon transducer versus the thermal transducers. And we're going to know each of them one by one. So we're going to look at the so-called photon transducer. Now, if we're going to look at this, what we call different detector types, so this figure shows us, okay, the relative response of the various photoelectric transducer. So A that you have here, that's what? A photomultiplier, PMT. Okay, letter B here is a cadmium selenide photoconductivity. Now C here would be a gallium arsenic photovoltaic cell. Photovoltaic. Now the D that you have here, this is a cadmium selenide photoconductivity cell. So this cadmium here is what? Cadmium sulfide. That's a photoconductivity. Now, E here would be your selenium oxide photovoltaic cell. Okay, F here is your silicon photodiode. And G here is your what we call lead sulfide photoconductivity. Now, these all are what? These are your photoelectric transducer or photon transducer. Now, the H and the I there, that are both your what? Heat transducer. So your H is a thermocouple, and your I is what we call a Golgi cell. So that's, we could say, the relative response of the various photoelectric transducer. So if we're going to look at this photon transducer, so usually they respond to incident photon rate, okay? And they are highly variable spectral response determined by photosensitivity of the material. So you can see it here. So some of them high, like the PMT and photoconductivity, some of them are what we call low. So there's a variation in the what we call the spectral response that they have. It responds quickly, microseconds or faster. Okay, it's used. It's a single or a multi-channel stop, and used largely for the measurement of the UVBs. So the photo transducers are not applicable in infrared because photons in this region lack the energy to cause photo emissions of the electrons. And the photo transducers that you have are either what? Photovoltaic cells, phototubes, PMT, photoconductivity transducer, silicon photodiode, and charge transfer transducer. Okay, so we're going to go on them one by one. Okay, so I would say the principle of the photon transducer, they detect photons, which are particles of light or electromagnetic radiation, and then they convert the energy carried by photons into electrical signals. Now, you use it commonly in optical sensors. Aside from that, you can use it in solar panels and the camera. Okay, so if we're going to look at the different example here, so one of them is the so-called photovoltaic cell. So this is a simple device that is used for detecting radiation in the visible region. So if we're going to look at it, it's consisted of a metal, semiconductor, metal sandwiches. Okay, so there's a semiconductor that, or a semi-metal that is sandwiched by two metals. So you have here the iron metal and a thin layer of this, what we call the silver metal. So if you're going to look at this, this is a typical cell that has a maximum sensitivity at around what, 550 nanometer. Maybe we can look at this one here. You see that? Where's the voltaic battery here? This one around here. Okay. So if you're going to look at this like this selenium oxide photovoltaic cell, so it's around 550, the maximum sensitivity. And they would really fall 10% of the maximum at 350 and 750 nanometers. So its range is just similar to our eye. Okay. So if you're going to look at this, the photovoltaic cells consists of a flat copper or iron electrode, which is in case is iron, which is deposited on which you deposit a semiconducting material, in this case selenium. Okay, so the outer surface of the semiconductor is coated with a thin transparent metallic film of silver. And you can also use what aside from silver? Gold. And they serve as the second or collector electrode. So if you remember your what we call analytical thing, so you could see here, okay, that these are just the electrodes that you have. I hope you see this one is on this one, and this one is on that one. Okay, so the entire array is protected by a transparent envelope, and when radiation of sufficient energy reaches the semiconductor, the electrons and the holes are formed, and the electrons that have been promoted to the conduction, okay, migrate toward the metallic film, and the holes toward the base on which the semiconductor is deposited. Okay, current is produced at the interface of the semiconductor layer, and the metal is proportional to the number of photons that strike the semiconductor surface. Okay, so if you're going to look at this one, the currents produced by photovoltaic cells are usually large enough to be measured with a microammeter. Okay. So for routine analysis, this we could say transducer often provide reliable analytical data. Okay. So this is what we call the photovoltaic cell. Now, the next one that we have here is what we call the phototubes. So this is the second type of this what we call photoelectric device. So we call it the phototubes or the vacuum phototubes. Okay. So if you're going to look at this, what we call the phototubes, they consist of a semi-cylindrical electrode that can readily give electrons when it is irradiated. So again, you have here what? An electrode, a cathode, and then an anode, and then there's what? A photon in the form of light. So what does it do? Okay. So when you apply a voltage there across the electrode, it emitted electrons flow to the anode, generating a photocurrent. So this is just an application of what? The photoelectric effect. Okay. So photocathode surface can be bialkali or multi-alkali. So that means sodium, calcium, cesium, sodium, potassium, cesium, strontium. And the wavelength response depends on the cathode material from 200 to 1,000 nanometer. So the current that is produced is proportional to the number of photons that strike the semiconductor surface when the saturation voltage is achieved, which is around what? 90 volts. Okay. Now, if we're going to look at this, what we call the phototubes, okay, there are a variety of materials or photoemissive surfaces that are commercially available. But it's not, as we could say, popular as some of the other photon transducer. So in some, they call these phototubes as phototube detectors or phototubes sensors. Okay, so they detect and measure the light intensity. So they operate based on the photoelectric effect. I think most of the photo transducer that we discussed in here, they operate on the principles of the photoelectric effect. Okay, the one that we have discussed earlier here, the photovoltaic cell, I think that is also similar to this one. So the way that you look at, you have a phototube here of photosensitive cathode, then you have an anode and a vacuum filled. Okay, that's why in some they call it vacuum phototubes. So when the light photons strike the photosensitive cathode, they eject the electrons to the photoelectric effect, and these emitted electrons are accelerated toward the anode by an electric field resulting in a measurable current. Okay? And then we have the so-called PMT. The photon multiplier tube. Okay? So if we're going to look at this photon multiplier tube, these are just like the phototube that contains a photosensitive cathode and a collection, okay, anode. So it's similar to that of the phototube. However, the PMT are what? More developed version of the phototube. So the anode and the cathode here are separated by electrons that you call what? Dinodes. So there's an irradiation of photoemissive cathode produces electrons, and a series of anodes or the dinodes increases gain to 10 to the 6, 10 to the 7 electrons per photon. Okay? So if you're going to look at the typical CMT, this is how it looks like. It still exists. Okay? So if you're going to look at this PMT, there are vacuum tubes that amplify the current produced by the incident light. So you have a photocathode, a series of diodes, and an anode. So what happened? Okay. What happened here? So this is a typical what we call photomultiplier tube. That's a commercial PMT. And then if you're going to look at this, this is the cross-sectional view of your PMT. And this is the electrical diagram illustrating dynode polarization and the photocurrent measurement. Okay, so if you have a cathode here, you have an anode here, and then that's what we call the dynode. So what happened, okay, when radiation strikes at the photosensitive cathode, it gives rise to photoelectrons. So once you have the light going here, so what happens? So where's D1? Okay, so dynode D1 to D9. So once there's a radiation there, so as you could see, it goes what? To D1, so they are aligned here. Okay, so radiation striking the photosensitive cathode gives rise to photoelectrons by the photoelectric effect. So the dynode 1 is held at the positive voltage with respect to the photocathode. Now the electrons emitted by the cathode are attracted to the first dynode, and then several electrodes for each incident electron. So it goes dynode 2, dynode 3, dynode 4. So each electron striking dynode D1 gives rise to 2 to 4 secondary electrons that are attracted to dynode 2, which again positive with respect to dynode 1. And as you go from one dynode to another, what happens? You amplify the signal until it reaches what? The anode, where you already have 10 to the 7 electrodes for each of these photons. So we could say that's the basic principle that we have in the PMT. Okay? When photons strike the photocathode, they emit electrons with the photoelectric effect, and this electron then accelerated and multiplies to the series of the dinodes. They are highly sensitive to low levels of light and capable of detecting single photons. And they often used in application requiring high sensitivity like fluorescence spectroscopy and low light imaging. I think that's the first part of the instrument that I broke when I was in grad school. Why? Because I hit it with laser and through that burn. See how sensitive it is. So instead of radiation, you have a laser. Sabog siya. So they're extremely sensitive, used for low application, light strike to photocathode, bias applied. So if you're going to look at this, the drawback that it has, sensitivity usually limited by the dark current, which is the current generated by thermal emission of electrons in the absence of light. Okay, so I told you, when you emit electrons, there's also some heat that it emits. And how do you remove this thermal emission? You use cooling. That's why when we use laser, if we have biological stuff, meron kaming tinatawag na temperature set up to make sure that it is at least cold condition. Okay, so under optimal condition, it can detect single photon. So you only use it for low light application. It's possible to fry the photocathode. Sometimes you learn when you break stuff. But the thing is, you have to face the mistakes you have or the error that you have. And anong kapalit doon? Well, my professor yelled at me, but after that, fine. Either you take it personally or you take it like it's a learning experience. Okay. And then we also have the photodiode. So this is what we call the PDA. Because it is really what? The photodiode array. Okay. So the silicon photodiode. So here you have the individual photosensitive elements, small silicon photodiodes, each which consists of the reverse bias proton-nitrogen junction. Okay, so it consists of the reverse bias, the proton-nitrogen junction formed on the silicon chip. So if you're going to look at the reverse bias that you have here, so this is how, okay, it looks like. So this is how the schematic of your silicon diode. Okay, so the formation of the depletion layer, which prevents loss of electricity under the reverse bias. So you create, when you have a reverse bias, you create a depletion layer that reduces the conductance of the junction to nearly zero. Okay, so if the radiation impinges on the chip, however, hole and electrons are formed in the depletion layer and swept through the device to produce a current that is proportional to the radiant power. They only require low voltage power supplies or can be operated under zero bias, so it can be used in portable battery-powered instruments. More sensitive than phototubes, but less sensitive than PNP. And you can use it from 190 to 1100. Okay, so what we have now are, we could say, the multi-photon transducer. So when we have what we call the multi-photon transducer, it's made up of one. Okay. So from the silicon photodiode transducer, if you have many of them, you can do this so-called PDA. So the modern multi-channel transducers consist of an array of small photosensitive elements arranged either linearly or in two-dimension pattern on a single semiconductor chip. So the semiconductor really advanced the technology that we have here. Okay, so the chip that you have here, which is usually silicon, typically has a dimension on a few millimeters on a side, and also contains electronic circuitry to provide an output signal from each of the elements, either sequentially or simultaneously. So for spectroscopic study, usually these are what we call useful. A multi-channel transducer is generally placed in the focal plane of a spectrometer so that various elements of the dispersed spectrum can be transduced and measured simultaneously. And you have six types of them: PDA, CID, and PCD. And all of them we could say are what we call useful. Look at my list. So the PDA that we have so they are linear arrays of silicon diodes consist of the reverse bias p-n junction. So we could say this is just the multiple version of the silicon photodiode transducer. So they have a series of that. So the number of these linear diodes used in between photodiode arrays varies between 64 to 4096 with 1024 silicon diodes at the most common. So each element consists of a diffuse p-type bar in an n-type silicon substrate to give a surface region that consists of a series of side-by-side elements that have a typical dimension of 2.5 by 0.025 millimeter. So if you're going to look, okay, at this what we call reverse bias linear diode array detector. So this is how it looks like. Okay, so this is the cross section, and this is what we call the top view. So it's an alternating PN thing. Okay. Now, in using this what we call diode array transducer, the slit width of the spectrometer is usually adjusted so that the image of the entrance slit just fills the surface area of the diode that makes up the array. Now, although this is useful, but it's not as sensitive as the what we call TMT with respect to sensitivity, dynamic range, and signal to noise ratio. So they have been used for application in which high sensitivity and large dynamic range is not needed. Okay. And the way that we use it is for the absorption spectrometry. So yan usually yung detector sa UVB. CCD, as they call it. Okay. Now, this is how the schematic would look like for a photodiode array detector chip. A simplified, we could say, diagram that shows the arrangement of this component. So you could see that there is what? Photodiode here, okay? Parallel with each photodiode. So photodiode, 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 they're just in parallel form. Okay, so this is not as good as the PMT because you see how many diodes you have here, and the principle that you have here is not similar to the one that you have, although both of them has this so-called photoelectric effect. Now, another thing that you have is the so-called charge transfer device. So the PDA, they cannot match the performance of the PMT with respect to sensitivity, dynamic range, and signal to noise ratio. On the other hand, the performance characteristics of your CTD approach or sometimes surface PMT. Okay. And in addition to having the multi-channel advantage, PMT kasi single channel lang. Okay. So if you're going to look at this one, there's an advantage of this CTD compared to the PMT. Okay. So a further advantage that you have is what? A two-dimensional, in the sense that individual transistor elements are arranged in rows and columns. Okay. So here, if we're going to look at this, it operates like a photographic film in the sense that they integrate signal information as radiation strikes them. I'm not sure. So if you're going to look at here, so this is a cross section of your charge transfer device in the charge integration mode. So the positive hole that you see here produced by the photon HB, so it's a positive hole, okay, is collected under the negative electrode. Okay, so the charge transfer devices, the charges developed in a silicon crystal as a result of the absorption of photons, they're collected and measured. And as you could see, it can match and sometimes surpass the PMT. It offers great sensitivity and high resolution to low light detection. And if we're going to look at this, what we call CTD, they're important, especially if you're looking for multi-channel detection, the spatial resolution, the so-called two-dimensional array. So its sensitivity is almost the same as the PMT, and an entire spectrum can be recorded as a snapshot without scanning. So integrate signals as a photon strikes the element. So the good thing about here, the pixel, okay, that it has two conductive electrodes over an insulating material, which is the silicon dioxide. So this insulator separates electrodes from the end of silicon. So if you're going to look at this, a semiconductor capacitor, it stores charges that are formed when photons strike the doped silicon, and it can produce 10 to the 5th to 10 to the 6th charges of pixel per pixel can be expelled, which is almost close to the 10 to the 7 electrons that PMT generates. So how is the amount of charge measured? For the CID, voltage change that occur from the charge moving between the electrodes. For the CCD, the charge is moved to an amplifier. And if we're going to look at an example of this one, so this is, we could say, a cycle, a duty cycle of your CID. Okay, so here you have what? The production and storage of the charge. Okay, and this would lead to the first charge measurement. So there's a change formation and integration, so that results in the production and storage of a charge. So you see there, your radiation goes here. So there's a production and storage of the charge, and then it looks to the first charge measurement, okay? And then the second charge measurement after the charge transfer. And this one, we could look at the re-injection of charge into the semiconductor. So this is what we call the duty cycle of CID. Now, this on the other hand is what? This is your CCD array. So in the charge coupled device that you could see there, okay, so what happened here, there's an arrangement of what? 512 by 320 pixels. And this is the schematic showing the 4 individual detectors. that you have. Okay. So if you note in this case, the photo or the semiconductor is formed from the P-type silicon. And the capacitor is biased positively so that the electrons formed by the absorption of radiation collect in the potential window below the electron and holes move away from the N-type layer towards the substrate. And we could say this is the so-called constellation image of an inductively coupled plasma emission. If you have 200 microgram of Fe per ml seen by CID. So almost all peaks are from the iron. Okay, so this is an iron here, iron, iron, iron. So you could see this is like a plate. So these are what we call photon transducer. So the next steps that we have are the thermal transducer. So wherein the radiation impinges on and is absorbed by a small black body and the temperature rise is measured. So this is in terms of heat. Okay, so you respond to the incident energy rate. And the sense is to change in temperature that is produced by the absorption of light. So we could say the signal has something to do with the change in temperature from the applied radiation. Okay, and as you could see, it really have what? A flat spectral response. And this is determined by window and the coating material. Unlike photon transducer, they respond slower in milliseconds. And it's a single channel. So you use it largely for the IR. And it's always an issue with thermal noise. Okay, housing in a vacuum, shielding, and cooling. And the one that you have in this, we could say, portion is the thermocouples, the bolometers, and the pyroelectric transducer. So the most sensitive thermal transducer in the near IR is your photoconductivity transducer. So what's the difference of this compared to this one? Kamali ako ng ano. Okay, dapat it goes before that one because there's still another special case, or maybe I'll put it together. So if you have the thermocouples, so these are the junction thermometers. Okay, so thermocouple, you have a pair of junctions formed when two pieces of metal, such as copper, are fused to each end of a dissimilar metal, such as what we call an iron, as shown in this what we call figure. So you have a copper here, positive, negative, and then you match it with the iron. Okay, so there's a voltage that develops. Remember the junction, the difference in the potential. Okay, so a well-designed thermocouple is capable of responding to temperature difference of 10 to the negative 6. The problem with thermocouples, they're cheap, slow, and insensitive. So you use it for IR. Now, the next one that you have is a bolometer. So if the first one is a junction thermometer, bolometers are what we call resistance thermometers. So this is a type of a resistance thermometer consistent of strips of metals such as platinum, nickel, and a semiconductor. Okay, and you always often call semiconductor bolometers or thermistors. So these materials exhibit a relatively large change in resistance as a function of the temperature. Okay, so you measure the change in temperature as resistance. Okay, and the responsive element is kept small and blackened to absorb radiant heat. They are not commonly used, okay, as the other what we call infrared transducer and mid-infrared region. However, your germanium bolometer operated at 1.5 Kelvin is clearly an ideal transducer for radiations in the 5 to 400 wave number. And the last that we have here is the pyroelectric transducer. So they are constructed from a single crystalline wafers called the pyroelectric material. So some of these pyroelectric materials that you have is triglycol sulfate, sulfuric acid, the deuterated one with the fraction of the glycine. So they use it in the construction of, again, IR transducer. So when an electric field is applied to any dielectric material, usually electric polarization takes place and the magnitude is a function of the dielectric constant of the material. So for most dielectric, you want this induced polarization to decay rapidly to zero when the external field is removed. Okay, so the pyroelectric transducer, they exhibit response times that are fast enough to allow them to track the changes in the time domain. So they are using what? Time domain from an interferometer. So for this reason, you use it in Fourier transform IR, or the so-called FT IR. Now, the other type of this, what we call transducer, that is neither photon or thermal transducer, is the so-called photoconductivity. So this is the most sensitive transducer for monitoring radiation in the near IR. Okay, so they are semiconductors. Resistance decrease when they absorb radiation within crystals. The application of this is in the FTIR, okay, wherein crystalline semiconductors form from the sulfide, selenides, and stibnites, such as lead, cadmium, gallium, and indium. So the way that it works is absorption of radiation promotes some of their bound electrons in energy states, which they are free to conduct electricity. Lead sulfide is the most widely used photoconductive material and can use at what? The room temperature. The lead sulfide is sensitive in the region between 0.8 to 3 micrometer. So those are the different what we call transducer. And once you have the transducer, once it passes through the detector, what do you have? You have the so-called readout system, the signal processor. Okay, so what does the signal processor do? It amplifies the electrical signal from the transducer. Okay, so it may change the signal from direct current to alternate current or the other way around, change the phase of the signal, and filter it to remove unwanted components. And the signal processor may be called upon to perform what? Mathematical operations on the signal, such as differentiation. You subtract the reading from your sample with the blank, integration, or conversion to a logarithm. So the several types of the readout systems are what? The digital meters. What else? LCD, right? Liquid crystal display, computer display. Now, how about the old one? What do you have? Analog meters, analog recorders, or CRT, cathode ray tubes, as your what we call readout device. Now, in addition to this, there's a term that they called what? Photon counting. Okay, so this is a technique that they use to detect and count individual photons, which are tiny particles of light. So instead of measuring the light intensity continuously, what does it do? It involves counting how many photons are detected within a period of time. Okay, so they used it for many years in X-ray, radioactive species, okay, usually in PMT. The way I used it is total counting single photon, TCSPC, some sort of, okay? And the advantage of this, what we call photon counting, is it improves the signal to noise ratio. Sensitivity to low radiation levels, improved precision for a given measurement of time, and lowered sensitivity to the PMT voltage and temperature fluctuation. So I think I'll end here. Okay. So we're almost done. So fiber optics, and then the type of this one, and then after this we go with atomic absorption. So question, I'm not going to give you anything so you can enjoy your break, right? Is this the only break that we have this semester, reading break?